Should we get started? Questions. Same questions. So, what do you remember from yesterday? A few things? Just fire.
I thought a lot of research is required to overcome the Indian standard law.
Absolutely. I agree. 100% I agree. Lot of research is needed. And you are all going to do that. All young people, you are going to do that. Oh, no, no. You should never say we cannot. You should always try. It is possible. Yes. Can you speak up? Come up. Is this working? Yeah, there should be. It is. Is this working? Come code. Is this working? Okay. Yeah. Can you speak loud so everyone can hear what you're saying?
We have to initiate our flexible design by green check instead of.
Absolutely. That's a very important design consideration. In many cases, it may govern. Anything else?
ACI uses action-based strength reduction vector instead of vector material based.
Yes. So there is a difference between IS 456 strength reduction factors, or not IS 456 is material factors, and in ACI strength reduction factor based on actions. Shear 0.75 for beam 6.65.9. Very good. Anything else you remember you want to say here?
We have to design for overkill.
Always design. That's a very good point. Actually, that's one of the most important. We always design beams. Are you able to?
Yes.
We always need to design our beams for over reinforcement. Perfect. Anything else you want to say? Something? Some from that call? Just say something.
Stress
No. You know, sorry. Yeah. Yes, please. Say something. Just something. Whatever you remember. Doesn't matter.
When the concrete strength is larger,
You have to speak loud.
when the concrete strength is larger, as the concrete strength is more, the section becomes, which we are designing as the over-reinforced section, it becomes an under-reinforced section.
I am so glad you remember that. Does anyone else remember that?
Yes.
Very good. So, if the concrete strength in the actual structure is larger than what we designed for, then it becomes under-reinforced. Very good point. I wrote that. Anything else?
We cannot design it as a moment resisting frame.
Yes, you cannot use FRP bars in movement resisting frames, or you cannot, and also you cannot do any movement redistribution. Perfect. One more. Say something.
TRP bars in tunneling system,
Yes.
we are including it because the spacing can be reduced to high strength. And since it is more reinforced, rather than a reinforcement bar, here unexpected load, these can take good loads. So
Yes.
we have been using TRP bars, wherein the number of bars are reduced.
Okay.
Reinforced bars are reduced, and TRP bars to give a quick.
Very good. Yeah,
Immediate
and also
support.
light. So lightweight. So particularly if the tunnels are deep inside, you can carry all the material right to the tunnel location. So it is cheaper or expensive to take the material from the surface to wherever you are doing tunnels. You know, that becomes more advantageous. Excellent. So we'll go over a few. We'll go over this quiz just quickly. True or false? Steel reinforced concrete beams are preferred to be designed to fail by under reinforced condition. Yes? Yes. I think this is too basic for you. I should have made it very difficult. But then I can't answer it myself. So what's the point? Right? Number 2, FRP reinforced concrete beams fail in a very ductile manner because of the linear stress strain. Thank you. We already talked about moment redistribution. Moment redistribution is not permitted in rectangular rigid frame structures. Yes, very good. It's preferable to design FRP reinforced concrete beams to fail by crushing of concrete rather than tensile. True. In an axially loaded bridge, there is a mistake, but anyway, in axially loaded bridge columns, it is allowed to consider compressive strength contribution from FRP longitudinal bars. No. Okay, in the context of steel reinforced concrete beam, tension control failure. This is something, it's kind of tricky, but tell me what it is. What is tension control failure? Under reinforced is fine. I'm fine with that. Yes, yes, but there is something very specific to tension control failure. No, greater. Okay, but you did not tell me what the limit is. 0.005. That's very important. We need to remember that. I mean, at least pay like it's 0.005. And that strain is at the level of the bottommost layer of steel. That's important, epsilon T. So that's if my strain in the bottommost layer of steel is at least 0.005, then it is considered to be tension control failure. What about compression control failure? Again, it's strain related. So what is the limit? Okay, I think I had a few answers. I want to explain that. Okay, explain something. So, in case of steel reinforced concrete beams, this tension control failure, compression control failure, both relate to strain in the lowermost layer of steel. Because yes, so for tension control condition, it's 0.005. Okay, which we all agree. Somebody said 0.0035. That's strain in concrete at crushing. So we are not looking at concrete strain. We are looking at steel strain. Okay. So in case of compression control failure, the strain is less than or equal to yield strain of the bars. Okay. That's what will classify a member to be compression control. In regular beams, we will never design a compression control beam. The reason for that is why? Do you remember? The maximum reinforcement is based on strain of 0.004. So your strain cannot be less than 0.004 for beams. Therefore, we will never ever in a new design a member to be compression controlled member. Okay. However, in columns where there is axial load and moment, beam columns, it may so happen we will use compression control condition. But for new beams, it's not allowed. You have to use minimum, or you have to introduce minimum ductility based on minimum tensile strain of 0.004. Okay. Only then we classify the member to be a beam. In the context of FRP reinforced concrete beam design, explain what is guaranteed tensile strength of FRP bars. Guaranteed tensile strength. For that test, for tests, many times like in concrete industry, they have standard deviation for labs. Each lab has its own standard deviation based on thousands of tests they do. They have their own standard deviation for material testing. But in FRP bars, we normally won't have that kind of database. So you have to create your own database. So here I will ask you a question. If you are going to use that guaranteed tensile strength equals average tensile strength minus 3 times sigma, what is the minimum number of bars you must test?
25.
Good, 25. That 3 sigma is based on 25 test specimens, okay? So if it is less than that, you may have to adjust your standard deviation a little bit. Very nice. Okay, what about the tensile strain? Same thing. Guaranteed tensile strain equals average tensile strain minus 3 times standard deviation. What about modulus? Guaranteed modulus is equal to average modulus minus 3 times sigma, right? No? No? Oh, you're all awake. Very good. I am so glad you're awake. Modulus, no. We don't use standard deviation. Perfect. So this is the tricky question. Mainly for those of you who are, doing research. And most of you are, because either most of you are PhD students or already professors teaching. So, in your judgment, what is a suitable partial safety factor for FRP materials when designing an FRP reinforced concrete beam so as to be consistent with IS 456? What do you think? What do you think? Let's go back step by step. So steel is very ductile material, right? So we use 1.15 and we accept it. We say, okay, steel is partial material factor is safety factor for material is 1.15. What about concrete? 1.5. So FRP is a ductile material or a brittle material? Very brittle. So now that we know for ductile material we are using 1.15, for brittle material concrete we are using 1.5. The material factor or material safety factor for FRP should be closer to 1.15 or 1.5? 1.5. I would probably use 1.5. I don't know if you agree with me. You may use even larger value if you want. But I would use 1.5. Okay? This is a trick question. Next one. So, what is the reduction? You have to pay attention to the word. Reduction in steel, in design tensile strength of a bent bar with radius of 5 times diameter. What is it?
45.
See, that's where I said I'm confusing you. I'm confusing you. When you use that equation, what did you get? 55. So reduction is what? 45. Yes, 45. Very good. If you are taking a test in computer-based testing, CBT tests, if students are taking tests online, this is a trick question. They will click 55, but that's not reduction. Reduction is 45%. Okay. So you'll get. I mean, if it is multiple choice question, you are doing computer-based, you can get it wrong if you say it is 55. Okay, that's good. Now that I have your attention, I will start my next chapter, which is shear design. Very good. So how is the course going so far? You happy? It's worth your time. 1 week of time is a lot of time for anyone, for all of us, for me, for you, for Dr. Das, everybody. So we want to make sure you gain most out of this. That's why they even named the program GAIN. Right? We are gaining something out of this. Okay. So after the break, I will have maybe 3 presentations. I may not be able to do all 3 presentations, but I have. I have many presentations. All the time we keep presenting, so we have many presentations. But I picked one. Dr. Das asked me to pick one on bridge beams. So I picked one. Many of you talked about fiber reinforced concrete with crack and corrosion. I picked one on that. And I also picked something on basalt fiber reinforced not exactly FRP bars, but it's a different product. It's called mini bar. I was right from the beginning. We developed it together with the sponsor, so I can show you some slides on that. So three presentations will take a lot of time. So what will be your top choices? Bridge beams,
box beams, slab bridges, and FRP minibar. Which minibar first? Minibar is your choice. Slabs, box beams, all are interesting. You'll really you'll enjoy it. But let's see. We'll do something. I'll go faster. I will skip every other slide. How about that? Then you will get nothing. Actually, this is exactly what happened to my students once. I had 120 pages of some report. I printed all of that, all the reports for my about 20 students. I gave them copies. So after 2 weeks, I asked, how is it going? Did you read the report? Nobody said anything. I said, have you read it? Nobody said anything. But before they could answer that, I knew they did not read it. You know why? Because by mistake I did not print on the back side. So it only printed every other sheet. So they did not read, obviously, right? If they read it, then they would say, oh, every other sheet is missing. So this actually happened. So it's really funny. Okay, today's topics are two topics. One is shear design and the other one is bond strength, okay, or development strength or development length. So shear design for FRP bar reinforced concrete beams, almost similar. It's not same, but similar to steel reinforced concrete beams. However, we have a lot of differences in terms of mechanical properties, and the modulus is low, so that's a big problem for FRP. And linear behavior until failure is also a problem. Dowel action, we actually brought it up yesterday. Dowel action is a big problem because dowel action in concrete in FRP bars is based on shear, right? So that shear is dominated by matrix performance, and matrix is very weak. So dowel action will be contributing very little to the shear strength. And then, so all these factors will affect shear strength. Also, there is very little experience with failures. So failure is a very bad thing, of course, but failures also give us a lot of lessons. We learn from failures. Of course, that's the reason we test in the labs, so we fail everything in the lab instead of in service. So very little experience. Stirrups have the tendency to be affected by moisture. So you think it's FRP bar, so I can place it very close to the surface. But they also absorb a lot of moisture, so that's a problem. So if it is a severe environment, stirrups will have a problem. Plus, remember, this is one thing I would like to highlight because most of you are thinking in terms of research, so you should think in those terms. Steel modulus is 200,000, right, or 200 GPa. For example, glass fiber FRP modulus is only 40. So 40, 200, what's the factor? 5? Oh, 5, sorry. So 5, a factor of 5, okay. So for the same amount of load, the FRP bar will stretch not just more, 5 times. 5 times more, right? So that's the problem with FRP. So shear design is based on compatibility of diagonal crack and then the widening of the diagonal crack. If you have, let me go to the next slide and then I will explain that better. So that's a big problem. You are stretching it much more than you stretch the steel bars. Concrete can only stretch that much, right? After stretching a little bit, I have to define what little bit is. It will start cracking. So excessive cracking can also be a problem in terms of spalling. That's one. The other problem is, we'll go to the next slide and that will be very clear once I show you that slide. This one. So many of you can recognize this. This is the shear transfer mechanism for shear design in a steel reinforced concrete beam, right? This is the longitudinal bars, then there will be diagonal cracks. The diagonal crack, if you isolate one side of the crack, this is what you will see. These are the stirrups, and this is the diagonal crack. Normally this length from here to here is assumed same as your effective depth D. That's what our codes assume. And then we have some stirrups crossing the interface. We have dowel action, and then we have solid concrete here, uncracked concrete in compression area. So that will transfer some shear, and the stirrups will transfer some shear, and the aggregate interlock will transfer shear. So 4 mechanisms for shear transfer, right, in shear design of beams. Number one is due to this uncracked section. So in case of FRP reinforced concrete members, this is likely to be larger or smaller. If it is the same force, then it will be same depth, right? So there will be much change here. The dowel action, FRP dowel action is very not so good. It's very weak. So we lose some strength here. Okay. These stirrups, vertical reinforcement, shear reinforcement. If it is FRP reinforcement, then the strength is large. But there is a problem. I'll talk about that in a minute. Then you have aggregate interlock, right? So if you have very wide diagonal cracks, you will have no aggregate interlock at all, right? Because for the aggregate interlock shear resistance to develop, you need to have frictional resistance. That means you should have very small opening, and the one side of the crack will ride, it will slide on the other side of the crack. That's what will give you frictional resistance, which is the aggregate interlock contribution. If you have this reinforcement, if it is FRP, you will have larger elongations. Larger elongation means larger diagonal crack. That means they will lose contact. That means one side of the crack will not be in contact with the other side. Therefore, there is no aggregate interlock. So that will reduce your shear resistance. Dowel bars will reduce your shear resistance. And then this may not make much difference. The other thing we have is the vertical shear reinforcement, which is, if made from FRP, that will be very strong, but we can only allow certain amount of crack opening here. Because of that, why? Number one, why do we want to limit the crack widening? Because you need to keep this integral. That means the whole thing should act like a beam, not like two pieces of concrete blocks. Okay? So because of that, we need to make sure that the capacity of the concrete to crack and maintain shear transfer capacity should be maintained. That means the crack widths cannot be very large. Because of that requirement, the ACI code limits the strain in the shear reinforcement to 0.004. 0.004. Again, I am repeating, 0.004. Okay, so you will understand the significance of that if I give you some numbers. 0.004. We already have that number here. Our modulus is, let's say, 40 GPa. 40 GPa. 40 GPa is the modulus. So what will be the force? Let's say times 1000. So what would be that? 16,000. Oh no, how much is it? 160. 160. If I had a steel stirrup, what would that be? much more than, or it could be close to 400 MPa, right? 415, that's the maximum anyway. So you are losing strength here because of the crack width limitation. So what I am highlighting here is there are many advantages to FRP reinforcement in reinforced concrete, but there are also many limitations. As long as you address all these limitations, you can design your FRP reinforced beams, no problem. But this is a big limitation, and because of this, your shear capacity of FRP reinforced beams is very small. Okay. So now I will just quickly present the ACI method for shear design, because ACI 440 uses the same approach for FRP reinforced shear reinforcement. So what ACI says is the approach is very simple. It says total shear strength is equal to the contribution of concrete and the contribution of steel. That's all. VC plus VS concept. That's what they call it. VC plus VS concept. So first we will say what is the shear strength contribution from concrete. We will go back to this slide here. So everything other than these shear reinforcement contributions will be considered as V sub C. V sub C is because of this uncracked length, shear transfer in this uncracked section, number 1. Number 2, double action. Number 3, aggregate interlock. Okay, so 3. All these 3 are combined, and from test results they came up with a simple expression which is VC for steel reinforced concrete. VC equals 2 times square root of F prime C. Of course, that's in PSI units. So we'll talk about SI units in a minute. These numbers are very convenient to remember. That's the reason we keep that way. So first of all, VC, which is the contribution of shear from just concrete, double bars and or double action and the aggregate interlock, is 2 times VC. I don't think you can read this, but VC is 2 times square root of F prime C times shear area. So in case of steel reinforced concrete, what is the shear area? Shear area is in case of steel reinforced concrete beams, the shear area is defined as the distance from here to here, that is effective depth times the width. That is the shear area. I'm sure you are using it in your equation, same shear area. In FRP reinforced concrete beams, we will not use full depth, effective depth as the shear area. We will only use this depth. And what will that do to my shear resistance? Reduce it significantly. So that's one difference. So anyway, in case of steel reinforced concrete, the shear area is BW. Subscript W is for the web. So if you have a T-beam, you still consider only the web width as the width of your shear area. So 2 times square root of F prime C BWD, that's the shear area, right? That's your V sub C, concrete contribution. Then we have the requirements for, okay, let me back off. And then you can find out based just on equilibrium and based on how many stirrups are crossing the interface over a length of D, we can find out the contribution of Vs just based on equilibrium, just statics problem. So based on the static problem, V sub S is AV Fy, which is the force, times D over S. D over S will give you the number of stirrups, where D is the effective depth